and he is part of the Warsaw Python community, and he loves Linux and open source. So, and if you ever struggled with floating point numbers, behaving in weird ways, and numbers that tell you that they are not a number, that's what NaN stands for, then this talk will be for you. So, warm applause for Konrad. Thank you.
Thank you. Thank you very much. So, I'm Konrad Gawda, and this will be float, everything you wanted to know about, at least what I can fit in 30 minutes. As it was said, I'm a Python programmer and trainer, and I do work also for Orange Polska as cloud evangelist. That's surprising to many people, as Orange is a telecommunications company, but it turns out, yes, we have our own public cloud. This one is located in Poland. So if you would love to have a virtual machine with no charging for amount of data you send to internet, and you would like it to be located in Poland, well, you know whom to ask. Okay, one more thing about me that connects me to Switzerland is my great-grandfather, who was a scientist working at Bern University. So it's even bigger pleasure for me to now be here. Okay, but let's go to the floating point numbers. Why they are called floating point? It's the idea that you write some numbers, some digits, and then you can place a decimal dot in some specific place between those digits. In Python, floats do inherit from number, complex, and then real. And you can create an instance of one using a literal version, using directly class float, or as a result of some calculations. And to get to know them, we need to understand how they work. So we will go, if that's our cruising boats that we will cruise today, because they're floats. So, okay, so to understand them, we need to go deep into the machine room. And here is where the matrix starts. So in mostly all Python implementations, floats use IEEE 754 binary 64 variables also called sometimes double precision. And if we take a look at a CPython implementation, you see float is implemented like that. The mandatory object header and then double. And double in C means that it is binary 64, at least in this configuration that CPython uses. Okay, so how does it look inside the memory? If you use some techniques to look into Python memory, you can see that a float object has 24 bytes, but well, that's including the mandatory header. And it looks as a hex in memory, it looks like that, but let's strip out all the header, and you get something like that. That's a hex, but I would like to see binary representation. So there is a smart function for that, int from bytes, but we need to take care about bytes ordering in memory. So sys byte order is a wonderful constant that you would like to use, and doing some other small things to see the representation. So this is how exactly the double inside float looks like in the memory in binary. And that will be useful in a moment. And just to make things clear, because we'll be using different number representations. So the representation that normal people use is a decimal one, so with a base 10, and I will sometimes use that notation to mark that this is a base 10. What not normal people, but we, the programmers, like to use is a hexadecimal, so base 16. So that will be like that. And you could also use base 2, and this would be like that. And by the way, those all are the same number. And you can see that, well, you can use decimal point with hexadecimal or with binary numbers. Well, works completely the same as with base 10. Okay, so having said that, now I'm starting the most complicated slide of my presentation. If you bear with me with that, you'll be cool. So, as my great-grandfather was a scientist, he probably has used a scientific notation. At least he would do if he used programming at the time. So, how do you do scientific notation? Write some numbers, then a letter E, and then some numbers again. And it says, in this case, 9 times 10 with 13 zeros. Okay, quite a big number. And you can use more digits, like here it's also this 1 point something fraction multiplied by 10 with 10 times to the power of 6. So 1 and then 6 different digits. The last ones of them are zeros. Okay. I think that's cool. And that's a notation that you can use in Python and many other things. But there is something, let's say it's a convention, that you're only stating the first meaningful digit, then a dot, and the rest of them is fraction. So the same number that I've shown, you could also write like this with E3 or like this with E7. The convention is not to do that, just to use a first meaningful digit and then a dot, and use everything as a fractional part. And that will be useful in a moment. Okay, what about numbers lower than 1? Well, you can use negative exponent. So 10 to the power of minus 6. It's like dividing by 10 to the power of 6. Okay, but what about binary numbers? Because I would like you to understand how it's aligned in the memory. And memory, the best way to represent that is a binary representation. So could we translate that to a binary base? Well, sure we can. Just let's switch the E letter to some different one. Here it will be P, specifying that we will raise not 10, but 2 to some power. Well, as I said before, the decimal fractions, or rather binary fractions here, work completely the same as with any other base. So base 2 is cool. And we raise that number, we multiply it by 2 to some power. And in fact, this number is 52. Okay, but then how do you specify numbers below 1? Oh, you already know that. You use negative exponent. But wait a minute, we would like to write it down into memory. So in the memory, in this binary representation, we can use zeros and 1, but not the minus sign. So there are several ways to deal with that. And one way, and that was the way selected when designing those floating points, is let's agree upon some constant, and we'll always subtract that constant from something that is represented in memory. So that's still the same number, but this time we agreed upon that we will subtract 1000 from thing that is represented, that is saved in the memory. So instead of saving minus 101, we save in memory 11, and then we know there will be something subtracted from it. Okay, so far so good, but the last thing, it's optimizing things. Remember I told you that the convention is that we always use the first meaningful digit and then a decimal dot. Well, think about it. In decimal numbers, there were several digits that could be meaningful. And what about binary? There is only one meaningful digit, and that is 1. So you will always have 1 dot something something something. Putting away representing 0, which is different case. So we can make an optimization and just say that we will always assume that there is 1 in the beginning, and we will not save that 1 into memory, and thus saving 1 bit of memory. Isn't it wonderful? So if you survive that, you know the IEEE 754 binary 64 format. That's it. So you have that's the formula. One more thing that I did not talk about is how to represent numbers below 0, negative numbers. Well, this time we do not subtract anything. This time we have just a bit that tells us if it's negative or positive. We have the exponent and the fraction. And a fraction is also called sometimes significand. And look at this. It has 53 bits of information, but only 52 are stored. Yeah, here we optimize by this one little bit. Okay, I would like to pay the glory to Wilhelm Kahn, who was one of the major designers of this format and connected with it the mathematical floating point coprocessor, the standard that is used today in processors, and that we use also in Python. And coming back, I said there is an exponent. So you will normally just subtract from it a number that we agreed upon, and this in this standard it is 123, and then rise to this power. Well, it has also several other functions. If the exponent is zeros, all zeros, then the value stored in the float is 0. So we can do this optimization, saving this 1 bit, because 0 is stored using exponent. The normalized numbers are a different topic that doesn't matter to us very much. Okay, then there is a, let's say, normal area in which it really is an exponent. Funny thing is, if you'd like to raise the 2 to the power of 0, this is the value that will be stored in memory. Why? Well, because we subtract something from it. So this is the value that is, if we would like to store, for example, 1 in memory, this is what will be in the exponent. And that's the maximal exponent. Well, it's not whole filled with ones. Why? Because the exponent that is filled with ones is saved for special symbols that we will come back to later on. Okay, so this is what we have in memory, for example, and the gray one is the bit that is not stored, so I guess that will be easy. So what is that? What number? Okay, let me make it clear, simpler. This is minus or plus. This is exponent, and this is the fraction part. So what number is that? 0, of course, the exponent is 0. That's 0. Okay, so what number could that be? 1, exactly, because here we have 1 dot and all zeros, and the exponent is just the middle thing. Okay, so now we increase the exponent by 1, so what will be? It will be 2. Okay, then I'll skip some more advanced examples just to just to save time. And that's how it goes. I'll put in 1 again, and okay. And what could that be? Compare the exponent.
0.5.
Well, half. Yeah, it's half because the fraction is completely the same, but we decrease the exponent. So now we multiply 1 by 2 to minus 1. So we divide by 2. Okay, and we can get different numbers with that. Okay. You've already seen a hint. This is a very special number because this is 1/10, 1 divided by 10. And this is a nightmare because 1 divided by 10 is something that you use very often, and it doesn't have a finite representation in binary system. Well, that's a source of many problems, but that's something also floats handle. And that's just to check if you're not sleeping. So what number will that be? Minus 0.1. Yes, exactly. The only difference is the sign here. Okay. We've gone through the hard part, to the machine room. We can leave that and go to our cabin where we use Python. So as the programmers, we use float object that has several methods. We could use float.isInteger to see if that has some fractional part. We can use asInteger ratio, which will give us a fraction, one number to divide by other. And you already see perhaps a problem that is, or rather a feature that is seen here. Because we cannot represent 1 divided by 10 exactly, so this function gives you what it has. That's the true approximation that is stored in the memory. Okay, so one specific thing is, so why Python, when we divide 1 by 10, does not print something like that, which should if you divide those two numbers? Well, the printing functions, also including wrapper, are designed in a way that they round to the nearest decimal number within the range that the smallest bit differs. So you could say to the machine precision. So that's one thing worth keeping in mind, that the least significant bit can be rounded by printing. Okay. Floats have also hex and from hex. I never used that before preparing that presentation, but it seems it is something useful if you would like to have compatibility. This notation is designed in the IEEE specification. One quirky thing about it is that everything is hex, except that part, the exponent, which is in base 10. Well, strange, but people do use that. Okay, let's talk about precision. And that's one of the 3 important things I would like you to remember about after this presentation. And this thing is, you can dig into it by using sys.floatinfo, for example. It says what is the precision of the floating point numbers that we store in memory. And that's the thing that I would like you to remember is in yellow. It's 15 digits. So that's, you can write down 15 digits. Yes, I know those are not 15. You can write down 15 digits and then put a decimal dot somewhere between them. So, by the way, that's with floats. With ints, there is also a limit introduced in 2022. There is a quite useful function if you'd like to dig into the precision. It is called ULP, unit in the last place, which tells you what is the difference between a given number and the next one that you could write by increasing by only 1 bit. So let's check how it works. So I've prepared a small code to print what is the unit of last place for some numbers. And because I told you, you have 15 digits that you could 15 decimal digits you could store in memory. It goes around something to the times 10 to the power of 15, and then it decreases. So the bigger number you use, the smaller is the difference to the next number. And okay, it's fine because you have 10 to minus 12, 10 to minus 10. They're really small numbers. Then it gets to minus 6, minus 5, and then, well, it gets a little bit tricky, and then there is a point when you get 1. So and at this point, you can increase floating numbers only by 1, and then it goes even more interesting because you can increase by 2, by 4. So from that, you can take that any float within this area has int precision, and then it gets worse. So what's this area? You can write it down in several ways. The way I would like to remember is it's between 4.5 and 9. In Polish, I would say billiard. In most languages also. In English, you would say quadrillion. And in SE, it's peta. So if you're working with petabytes, for example, well, floats are starting to be tricky. Okay, let's go to special symbols, because you could store that in float. So remember when I was talking about exponent, if it's full with ones, you could store some special symbols, but not only this. Okay, and that's also from the IEEE specification. So infinity. Quite nice thing. There could be plus infinity and minus 1. There is a function to check if a number is infinite. The other thing, which is not so obvious, is minus 0. Oh, because the sign is a different thing. It has a separate bit. It means that 0 can be plus or minus. Oh, it's a bit strange, but normally no problems with that. And the last part is a problematic thing. It is none, not a number. And you can create it by parsing a string none with any case. And there are some functions for that, but Boolean of none is true. And any comparison, like equals, lower than, greater than, is false. And that's a second thing that I would like you to keep in memory. So that can lead to terrible things in a Python logic if you don't take caution with that. Not a number, all comparisons are negative. Okay, let's say something about rounding. And in fact, if you do mathematical operations, they're done on the coprocessor that uses IEEE standard, and this has several settings that are foreseen by the standard that tell you how the numbers will be rounded after doing some calculations. And in fact, you can dig into that in Python and change this mode. I don't know why, but perhaps you will have some point to that. And for example, divide 1 by 10, and in different modes, well, it gives a different result. Well, you'll say, great, Konrad, you get a difference of 1 bit. That's a wonderful thing. Well, it may be if you use numbers big enough. Remember the 9 quadrillion, 4 to half to 9? So after 9, the precision of int is 2. So in one mode, if I add 1, it does not change. In the other mode, it does change. So may be useful. Okay, that's rounding in the mathematical coprocessor. How it's in Python? Well, the function rounds, of course, rounds to full numbers, but it rounds to a nearest number. and to a nearest even number if two numbers are in the same distance. So that's the other thing I would like you to keep in memory, that rounding 1.5 and rounding 2.5 gives you the same result. There are other methods that will also produce rounded result. So if I would like to put them together on one slide, function round, if the distance is equal, goes to the even number. If you use double/division, it always goes down to -infinity. If you use int, it goes to 0. So it's difference when you're using negative numbers. And there is function math ceiling that always goes up. I will scroll a little bit faster because there are some simple things that we were talking about, but the thing that everybody waits for is to hear about the disasters. So here now, 91, Saudi Arabia, Patriot missile battery did not shoot at a Scud rocket. It's not that it missed, it just didn't fire at it. Why? Because the internal clock ticks every tenth of a second, and then, well, you need to multiply it by 0.1 and store it in a register which has 24 bits, so it's this magnitude of error. And the battery was running for 100 hours, so the error accumulated to 0.34 of a second, and that was enough to make an error in the calculations and say that, oh, this will not match. We did not need to fire a rocket. Okay, the other thing about rockets is Ariane 5, its first start, and that was a wonderful thing, but also a disaster. Oh, you see here, it's a ball of fire. And that happened not exactly about floats itself, it was about casting them into a smaller, lesser amount of bits, which caused overflow. And that resulted in it. Going further, there was also a disaster of a drilling rig, old drilling rig. It was attributed to a Nastran program written by NASA in Fortran, but there are no specific details. And the last one I would like to share is parliamentary elections in Schleswig-Holstein. The threshold to get to the parliament was 5%. The Green Party got 4.97%, and the printing function rounded that to 5%. And well, this function was used for years before. So when you're writing, so my conclusion, because I would like to conclude now, is if you need specific values, like with money, always stick to type decimal. If you need to compare if it's equal, then with floats, there is a lot of trouble. And if you're doing parliamentary elections, always test with edge cases. Okay. Okay. Thank you very much.
I guess you're loaded with questions, but sadly we don't really have time for them. I hope this is okay for you.
Well, I tried to answer all the things that people wanted to know, so okay. I guess you know everything.
So yeah, the next thing is the lunch. I mean, you can sit at the same table like speakers and ask me the questions there. So yeah.